Hi everyone, in this video we'll talk about the very famous problem or puzzle, if you may, that is called the Monty Hall simulation. And why is it called the Monty Hall problem is because you are given a choice for three doors in which one of the doors has a price and two other doors are empty, right? The name Monty Hall comes from Let's Make a Deal, where the host's name was Monty Hall, right? And the host used to give this problem to multiple people in the audience, and he used to ask them which door would you like to pick, and then he would open one of the door that does not contain the price and then give them the choice again later. Do you want to stay with your original choice or would you like to switch? This problem has emerged as a very famous problem for, for all the statisticians and for all the job interviews as well, and the answer is very something that a normal person would not even think of when they attempt the problem in the first go. So with that, I'll just dive into the video. In this video, we'll simulate the problem Monty Hall gives to an audience member like 10,000 times and see what the result will be based on the choices of that audience member. So right now the audience member is me, you, the viewer who's watching this video, and the problem giver is this code that I'll be running, right? Everything will be simulated. We'll simulate the problem in R to see what the result do we get. As always, before starting, clear the environment using rmlist is equal to ls and control plus L. Now, the problem statement, like I just showed you, there are three doors in the game show. Monty Hall comes up to you and says, one of them has a price, two of them don't. Please pick a door, right? Then, you know that it's three doors, one of them has a price, the basic probability is 33%. Let's say you pick door number one, right? And then what will happen? Let's simulate that basic normal scenario first to see if R gives us that 33% answer eventually, to see if our calculations are going correct. So first we'll simulate the simple problem of 1 in 3 by using R in a for loop. So first I'll set the seed to control the system randomization. Doors 1 to 3. I have 3 doors, so I'll initialize the counter for doors. And then I'll initialize the win counter, that how many times do I win when I select one of these doors. Okay, now we come into the for loop. Before I run the whole loop, I'll explain to you what's going on inside the brackets of the loop. Price in door. So I'll randomly select one of the price door. So there's a command called sample doors size is equal to 1. I'll run the sample command among doors 1, 2, 3, and I have to select one out of those 3 doors. So any random selection will happen here. So price in door can be 1, 2, or 3. Now what's my choice? My choice is door number 1. You can choose any one of the 3 doors, doesn't make a difference. If you are coding this in your R console, you can choose door number 2 or door number 3. I bet the answer will come out to be very similar or same in fact. Now, then I run an if command. If my choice is equal to price in door, let's say my choice is door number 1, and the sample command just throws out door number 1 as a price door as well, then I win, right? That's a good thing. Then the win counter will become win counter plus 1. It just adds up. And if I run this whole code for 10,000 times, the maximum my win counter can go up to is 10,000, right? Because initially it's 0. If it runs for the first time, I win, it will be 0 plus 1. If it runs for the second time, I win, it will be 0 plus 2, right? So I'm just repeating this chunk of code 10,000 times to see how many times does the win counter update itself, right? So I'll just run this code and it's run. It's showing me in the console. And now I will just print win counter, how many times did I win, divided by the number of times I ran the game. So it's 10,000 times I ran this game. My choice was 1 for all those 10,000 times, and now I'll find the win counter by 10,000 to get my probability of winning, right? So if I just type it out, this is probability of winning, and I run this and I get 34.24%. So if I choose door number 1 for 10,000 times and I don't change my choice at all, I will be winning approximately 33 to 34%. Now, of course, if you increase the simulations by, like, let's say 100,000 or 1 million or 1 billion, this number will converge to 33% more. In the interest of time, we'll focus on just 10,000 simulations, as I feel it's more than enough to reach where we want and to think about what we want to think, right? So now the basic game is done with. We know our basic loop works. We will win 33% of the time. mathematically that's the case as well. That should have happened eventually, right? Here in the summary, it's written, if you stick with your choice after the host opens an empty door, your probability of winning will remain 33% as shown above. If Monty Hall comes to you, says there are three doors, open one of them, you will say door number one. Okay, you win 33% of the time. Then if he opens one of door number 2 and 3 and shows you that it's empty, and then re-offers you the choice, would you like to stick with door number 1 or would you like to go with door number 2, right? Or with door number 3? Then is it in your interest to switch your choice? Do you want to switch it or do you not want to switch it? So if you stick with your choice, you will remain at 33% as shown above, because if you stick with a choice, it doesn't matter whether Monty Hall offers you the choice or not, right? Even if he did not offer you the choice, you would still have stuck with door number 1. But if he offers you the choice, now you have a conundrum. Should I go with the new door or should I stick with the new door, right? So there's a note here which I have tried to explain it in very simple terms. When you choose to not switch your choice of door, you neglected the extra information provided by the host, which immediately gives you an advantage in this game. That's the beauty of it, right? Now, let's say you chose to switch the remaining door. Let's say you chose door number 1 and door number 1 may or may not have the price, right? Monty Hall opens door number 3 and shows it's empty. Now, should you switch to door number 2? And what is the winning probability if you make that switch every time in 10,000 simulations? Is it more than 33%? Because if it's more than 33%, then you should make the switch every time this game happens. So let's try to first, code this in R and see how we can go behind it. Before we run the simulations, we need to create a function to switch. If you want to understand how this function is created, it's a very simple code. You can pause the video and type it out and see yourself how does it work. I mean, in a brief summary, if I have to explain it to you, it's just a function of doors, price in door and my choice. If my choice has the price in door, then Monty Hall can only reveal the door which does not have the price, right? And that will be randomly selected. Like, let's say I have door number 1 as my choice, and that door number 1 has the price. So now Monty has to choose between door number 2 and door number 3 to which door to open to reveal to me, right? So that this is what this doors to reveal function is doing. If I have chosen door number 1, price is in door number 2, then the choice for Monty to reveal is only one door, that is door number 3. So that's what the second command is doing. So you can pause the video, reflect on this function. This function is only helping Monty Hall to know which door to reveal. So this function is coded in R to simulate what Monty Hall would have done, right? Okay, now moving forward. What will be the winning probability if you switch every time you are offered a choice to do so? Now, set seat, we will control the randomization, win counter, and we'll initialize it again because now we are running the loop again. Okay, the simulation is again for 10,000 times. Price in door, doors are 1, 2, 3. One of the random doors will have a price. Our choice will still remain door number 1. I mean, why do we have to change it? This is the same as the previous loop. Now we'll use the reveal function that we coded in just the cell above. You can dial back to the video if you want to understand that function again. So this will help the host to reveal which door to show to us, right? So there are two doors, 1, 2, 3. Price is in one of the doors and my choice is one of the doors. So this tells which door to reveal. My choice is 1, reveal is done. Now new choice. Let's say I choose to switch every time. Let's just try it out. I mean, maybe the probability goes up, maybe it goes down. We'll see it in the results, right? Let simulations do their thing and us not think mathematically. That makes sense, right? A new choice will be the choice what we chose earlier. We cannot choose that again. And what's revealed to us, that's open. Why will we choose an empty door, right? So the only choice that left for us to switch to is the one door which is not our choice and not the revealed door. That's what this command is telling me to do. Now, again, it's an if command. If the price in door is equal to the new choice that we made, then just do a win counter is equal to win counter plus 1. And if I run this for 10,000 times, the maximum my win counter can go up to is 10,000, which gives me a winning probability of 100%. Of course, that won't happen, right? And now the function is run and we'll run the for loop again. The for loop is run and we'll run the print. So now it gives me 66.5% winning probability if I make the switch to new choice. Now, why is this happening, right? So mathematically, you can think when you had the original choice to choose between one of the three doors, you had a 33% chance of winning. Perfect. But you immediately had a 67% chance of choosing the wrong door, right? If you flip the sides and see, if you're choosing one of the three doors, you are 67% times going to be wrong. So your initial choice most likely has to be wrong. So when you're making choice, two out of three times you'll be wrong. So you have to assume that the first choice you made is wrong. And when Monty opens one of the remaining doors and offers you the choice, assuming you were wrong the first time, the choice is so much easier because you knew you were wrong when you selected door number one. Monty opened door number three, which has nothing in it. Then that gives you an implied odds that okay, if I switch, I'm right most of the time, right? Because if I'm wrong in the first go, and then Monty reduces the choices for me, I'm immediately right if I switch. So this is a thought that will take time to adhere to your brain. You might want to search some blogs to get the mathematical reason behind it. But if you just see a simple simulation run an hour, you can see that if you switch every time, you'll get a better odds of winning at this game, right? So simulations certainly help, and they will really really help even if you cannot crack it mathematically at your end. Now, just a note, most people believed when when you're offered a choice after revealing a door, the probability is 50-50 because you're choosing between the two doors. This is not certainly a case as simulations show it. That's because when you are offered the choice between two doors, you already have made one of the choices in between three doors. So your probability actually moves up when you switch, and our simulations certainly show that if you switch, you will win 67% of the time. Thanks for watching this video. I'll see you in the next one, and I hope you had fun in this. Thank you. Cheers.